So if I'm given a physical quantity with a number and a unit, and I don't like that unit, I know how to change it into the different number and the other unit that I want, just by multiplying by 1 a few times. But why would I prefer one unit over another? There are many reasons to do so. For example, as a unit of length, a rough isn't very good because there's no standard height for a Scottish Terrier, so it's very hard to check exactly how many roughs tall you are. And same with meows. It's very hard to stack cats to very high sort of piles, particularly above 2 or more. And so, why would I change to different units? Well, sometimes I'd like the numbers to be reasonable. I mean, I could take a very, very tiny unit of length, like a micron, and measure myself in microns, but I'll come out to be millions of them. And humans don't usually like carrying around really large numbers. You'll notice that when I started talking about 3.5 million joules in a previous example, I converted it to megajoules, because 3.6 is a kind of human-sized number. I can think of 3 things, or 4 things, or 3.5, but 3.5 million is just a little bit hard for me to conceptualize. And so we often change our units to try and make a more reasonable choice of number. The absolute easiest way to do this is to use the metric multipliers. So when we had 3.6 million joules, we already introduced the megajoule. So mega anything is a million of them, or 1 with 6 zeros. We're familiar with the kilometre being 1,000 meters, and indeed a kilo anything is 1,000 anythings. There's also hecto for 100 and deca for 10 and deci for a tenth. Probably the next most common one would be the centi. A centi something is a hundredth, e.g. a cent is a hundredth of a dollar. And we have milli. A millimeter is a thousandth of a meter, and milli is a thousandth of anything. We also have micro and nano below that, and giga and tera above that, and many more besides. Once you know those, and you know the symbols for these things, so giga is prefixed by a capital G, and mega is a capital M, and kilo is a little k, micro is the Greek symbol. So once you know those symbols, you can make up all sorts of units. Anytime you have a unit, you can always have a giga version of that unit, or a kilo, or a micro. So for example, we might have seen micrometers. So you know what a meter is, that's a micrometer, that's a millionth of a meter. You might know kilometers. You might be familiar with megahertz. A hertz is a unit of frequency, it's how many cycles per second, so a megahertz is a million cycles per second. Or in terms of computers, you might have heard of gigahertz. You might have heard of centimeters. You might have heard of milliliters. You might have heard of nanometers. So many of those examples were meters. But in fact, all those things could work just as well for joules. You can have megajoules or microjoules, or you could have megawatts, you could have gigawatt power stations, and so forth. So if you say that it's 1.04 megaroughs from here to Sydney, and you tell someone that, then they're not going to know what you're talking about, because they don't know what a rough is. And if you tell them it's the height of a Scottish Terrier, and they measure their Scottish Terrier, they may well get the wrong idea, because Scottish Terriers aren't very standard. And there's 2 important things you have to have in a standard system of units. The first is, it has to be easy to measure. And the second is, it has to be the same for everybody, so we all have to use the same units. And over the last few hundred years, people have moaned and negotiated and tried to get towards something, and we've done pretty well. So now, all countries in the world, except for 3, except for Burma, Liberia, and the United States of America, use what's known as the International System of Units, or the Système International, the SI units, the metric system. Now there are an enormous number of different SI units. And that's just a small sample of them, so don't be surprised if you don't recognize some of these, and there are many others besides. You almost certainly recognize the second and the kilogram, and the volt, and the hertz, and the meter, or the ohm, maybe, and the newton, but maybe you haven't heard of the Weber. And perhaps there's no surprise there's such a large number of units, and remember this is just a subset, because there's such a large number of different things we might want to measure. The weight of a swimming pool, the height of a tree, the pressure under a shoe heel, the conductance of a nerve, the speed of a bicycle, the brightness of a star, maybe the wind velocity. Of course, 2 of those are the same. So the speed of a bicycle and the wind velocity are both velocities. In other words, you both measure them in terms of distance over time. Now, one of the things that's done right in the metric system is that when you have a unit of velocity, it's not a completely independent thing from the units of distance and time. So we already have a unit of distance in the SI system, and that's the meter. And we already have a unit for time. And so the conversion becomes very simple when the SI unit for velocity is indeed the meter per second. And in fact, there are lots of relationships between all these different units. For example, a newton is a unit of force, and force, we will find, is equal to a mass times an acceleration, which is the same as a mass times a distance divided by time squared. And so the unit has got to be kilograms meters per second squared. And indeed, 1 newton is exactly 1 kilogram meter per second squared. So if I know what something is, if I know that a force is a mass times an acceleration, then I can figure out that the unit for force must be a kilogram meter per second squared. And I don't necessarily even have to know that that's called a newton. So you don't necessarily need the SI name, although it'll often have a name. All you really need to know is how it's built up of these other more fundamental things. And that powerful thinking can even go backwards. Sometimes if you know the unit very well, you can actually make a fairly good guess as to what that thing is. So for example, a pascal, which is a unit of pressure, if I tell you that that's 1 newton per meter squared, which we could turn again into kilograms and seconds and meters if we wanted to. But if you knew that, then you can kind of tell that it's a force per unit area. So newton is an amount of force, and meters squared is an amount of area. And indeed, pressure is how much force per unit area something has. So how many of the really fundamental quantities are there? Well, it turns out that nearly all of the SI units can be based off only 4. The kilogram, the second, the meter, and the coulomb. So there's this stuff called mass, there's this stuff called charge, coulomb is a unit of charge, there's this stuff called distance, and stuff called time. And out of those 4, you can build nearly all the others. The only exceptions are the candela, which has something about how the standard human eye responds to light, and the Kelvin, which has something to do with temperature. So these 4 fundamental quantities, and nearly all physical quantities are related to them. Because the SI units have to be designed to be easy to measure as well as standard for everybody, they don't actually contain these 4 fundamental quantities. They do contain the meter and the kilogram and the second, but the SI base units don't use the coulomb, they use the ampere, which is the unit of electric current. That's coulombs per second. That's the one that's defined because that's easier to measure, it turns out. There's also in the base units the Kelvin, mole, and the candela. And those base units can be combined to produce all the other SI units.